Hi everyone, welcome to Lecture 2 as part of the National Scale Fluvial Geomorphology Characterisation series, where we'll be looking at channel mobility analyses using remote sensing imagery. So here we provide a brief overview of what will be covered today. In Lecture 1 we focus on topographic analyses of the stream network and river catchment, and then we scaled that up to look at the National Philippine Geomorphology Database. In Lecture 2, we're going to use remotely sensed satellite imagery to start to assess channel mobility and river migration. So as you can see on the image on the right, rivers are particularly dynamic in the Philippines. So we're going to think about channel planform classification and the adjustment processes that take place in rivers and provide an overview of those processes. We'll take a planimetric perspective, so a top-down perspective to look down on the river to investigate some of these changes. We'll think about some of the available sources of data for planform change analyses. And then we'll start to think about how we can define the active river channel from multi-temporal, multispectral satellite imagery. So that means using collections of image classifications, so lots of images through time, and lots of different spectral bands that are part of satellite imagery. I'll provide a really brief overview of Google Earth Engine and how that can be applied in fluvial geomorphology applications, and then we'll provide some results and analysis looking at active river channel change for the Bislak catchment and the Cagayan River, before just mentioning a few limitations and uncertainties of the analysis. At the end of the presentation, I'll provide just a few take-home messages that will continue into Lecture 3. A working definition of what we mean by the channel planform. The channel planform is defined as the configuration of the river in plan view. So we're taking a top-down view, as you can see, a bird's eye perspective looking down onto the river, and we're classifying the channel based on the number of active channels, so whether we have a single thread or multiple active threads of the river, the sinuosity, so how sinuous or bending the river is going through, looking at the planform view, and also thinking about the lateral stability. So in this example, it's a river cutting through volcanic bedrock. We have a very high lateral stability. The channel isn't able to move across the valley bottom, whereas in the example here we have a braided system that has low lateral stability. The channel planform is able to move laterally across the valley floor. And the key point really is that the channel planform classification provides a reach scale summary of the channel and the floodplain characteristics. So it's a way of quickly classifying and summarising the channel and the floodplain. These aren't really discrete units. We get a continuum of channel planforms. So rivers can be on a spectrum of different channel planforms. We wouldn't have one unit compared to the other. And this is really conditioned by a combination of the hydrology, so the amount of discharge running through the system, the lithology or the geology, the bedrock, the sediments, and the biology as well, so vegetation cover effects. And as Richard introduced in Lecture 1, we have this channel evolution triangle where the channel planform is being controlled by the interplay of these three key factors. And here we take an example from the Bislak catchment in northwest Luzon. It's some of the analysis that PAMI has been leading to look at different river types or river styles in the Bislak catchment. And what we can see in a relatively small catchment, we have a real geodiversity of river types. So we move from the upstream headwaters of the catchment down to the outlets into the West Philippine Sea. And what we can see really is that in the upland areas we have this confined section with single active channel threads, so steep headwaters, gorge settings, with some very occasional floodplain pockets, but you can see the single channel. The red indicates the floodplain, and in the confined area we've got a very limited floodplain. As we move down the system, we transition into a partly confined setting, so the river has a little bit more space to adjust laterally and can expand out onto the valley bottom floor. So we have these pockets of floodplain which can have sediment deposited, but then as we move further downstream into the downstream sections, we've shifted into the laterally unconfined zone, so the river no longer abuts the valley setting, the valley sides, and can expand laterally and really spread out across the floodplain on the alluvial plains here, where we have a much wider floodplain unit. So in a relatively small catchment, we have a real geodiversity of channel planforms. So here we think about the different types of channel adjustment processes. So alluvial channels, those that have a sediment bed, can adjust both laterally in the width dimension, but also vertically in the depth dimension. So we have two principal dimensions of adjustment, laterally or vertically up and down. So thinking about lateral migration, this is the progressive adjustment of the channel across the valley floor. So the channel is eroding into sediments on the floodplain. It can adjust laterally at the edges of the channel, and in doing so it can expand, it can enlarge the active channel area in response to erosion at one or both of the banks, or the channel could, conversely, the channel could contract. So if we get deposition of sediment at the outer channel banks, the channel can narrow and contract. At the same time, the channel is able to incise or vertically degrade into the bed, lowering the bed elevation, and so that's channel incision. And likewise, if we have an abundance of sediment, we can get accumulations of sediment at the bed, and that can vertically aggrade the channel. So we have these competing channel adjustment processes that make the active channel quite dynamic. And it's the combination of the lateral and vertical processes that vary in different settings and at different times. So this means that channel adjustment processes can vary from reach to reach, so at different parts of the river, going downstream, we'll get different processes taking place, and different river types to different river types will also see a different combination of these processes. So in Lecture 2 and Lecture 3, the real focus is on lateral adjustment processes. So Richard does focus on the vertical changes in the geomorphic change detection workshop, but in this lecture and the practical exercises, we're really interested in taking the lateral perspective to measure planform or planimetric changes. And just as an example of this from the literature, here we see an example from Northern England, in the black and white image on the left, taking data from historical maps, aerial photographs, and remotely sent satellite imagery, and really trying to quantify the changes in channel planform through time. So at different time periods from 1844 onwards, here we can see real changes in the river morphology taking that planform perspective. So we see quite a complex channel pattern, channel planform initially, with large areas of active gravel and semi-vegetated gravel bars. We see as time progresses, the channel planform becomes less complex. We lose these active channel areas, the active channel bars, and we transition towards a single active channel thread. And this is the effect of anthropogenic activities. So this is a really heavily mined channel in Northern England, where aggregates, gravel has been removed from the system, and that's really altered the channel planform. The image on the right is taken from lots of satellite images put together, and what we can see for this tropical river in the Amazon, we can see real lateral adjustment processes taking place. So large-scale channel expansion, meander migration, and a really dynamic river system here. And what looking at channel planform allows is really the analysis of spatio-temporal trends. So what we mean by this is that we can look at the spatial dimension, so where in the river system the changes are taking place, and then we can also look at the temporal component as well. When are the changes taking place? So bringing together the spatial and the temporal can really help us understand the magnitude of change in river systems. And already some work has been carried out to try and quantify some of the active channel changes in the Philippines. So back in 2019, Lizzie Dingle calculated some river migration rates, particularly looking at meanders, focusing on the Cagayan River and one of the tributaries, and found that meander migration rates were very high. So rates of up to 30 meters per year, the meanders were migrating. And looking at the global scale, the Cagayan dataset in these tropical river systems, the migration rates plot very high compared to temperate rivers, where we tend to have more data available. And the rivers are dynamically adjusting to sediment and water fluxes, so these are the imposed boundary conditions. More discharge, more sediment can lead to more geomorphic activity, so more channel migration. But there are multiple factors that contribute towards lateral channel adjustment. So the importance of the hydrology, the opportunities for geomorphic change to take place during higher discharge events associated with the monsoon or tropical cyclones, changes in sediment supply, so lots of landsliding can introduce more sediment to the system. But then we also need to consider anthropogenic activities, so things like river training measures that can seek to control the planform of the channel. But you can just see from the Cagayan example that really large-scale geomorphic changes are taking place in some of the Philippine systems. And as part of Work Package 1, we're trying to scale up these analyses across the Philippines to different climatic settings, different tectonic settings, and different geological zones. So in this section we try and explain why channel mobility is important. The measurement of planform changes through time provides useful information on fluvial system dynamics and the magnitude and rates of channel change. So it's through the assessment of recent and historic planform change we can provide context for river management studies, so we can start to understand the behaviour of river systems and what we expect to see happen in a normal river system. But we must note that channel dynamism can really represent a geomorphic hazard. So this can be to critical infrastructure, an example here from Moussaka in Greece in September 2020. We have a before image, an after image, and we can see that riverbank erosion, lateral migration of the channel during this geomorphically effective event has led to the loss of critical infrastructure. This is a hospital that's now been eroded into the river. We see a lot of this activity taking place across the channel, so lots of places, the yellow arrows indicate where bank erosion has taken place. It also poses a risk to agricultural land, so we get a lot of loss of valuable, economically important agricultural land in different settings. So it's through the analysis of historical maps, aerial and satellite imagery, that we can start to study channel stability and river migration. But in studying river migration, we first of all need to define the part of the river system that we are interested in investigating. So there's lots of different definitions of the river corridor or the riverscape, but the river corridor is an inseparable unit consisting of river channels, fluvial deposits, riparian vegetation zones and floodplains. So we've got lots of interconnected elements in the river system, including the low flow channel, the active channel, the riparian vegetation and the floodplain, that all come together to make up the river corridor. And the key point really is that the envelope of the river corridor will be fuzzy. It changes in space and through time. So the active river channel is not fixed in position. So here we show an example from Gunnell et al. 2016 that deposition or erosion of matter can laterally and vertically change the active river channel position. So one of the key changes in river channel morphology would be between the low flow channel and the high flow channel. Here we show an example from the Abra River in Luzon, where the position, number and width of active channels changes between the dry and wet season. So the river looks morphologically different, and we might classify the planform differently between the wet and dry season. We can see that as the river flow stage increases, it inundates a greater area of the channel, the active channel, and that means it could alter our geomorphic interpretation. So because of the different river morphologies with increasing or decreasing river stage, an alternative is to classify the channel based on the bankful channel extent. So this is used to identify the physical boundaries of the river channel, and we can delineate the bankful channel extent independent of the river stage. So this assumes that any region or bank within the channel that has exposed sediment, it experiences flow and sediment transport frequently enough to inhibit vegetation growth. So therefore it experiences flow at a time interval that are common within the hydrological definition of bankful flow. So for tropical rivers, this occurs at least once every few years. So we see that the exposed sediment, here we are interested in the exposed sediment, the wetter channel, and the unvegetated parts of the channel system. And in defining the active channel, we have lots of different sources of data available to us. We have historical maps, generally ranging from the 1700s onwards. We have available aerial photography, so from potentially the 1930s or 40s to the present day. And we also have various forms of satellite remote sensing imagery, running approximately from the 1970s again to the present day. There's a real potential to integrate different data sets here and multiple sources of data. So we can integrate the historical maps with aerial photography, also satellite remote sensing. And geographical information systems, things like GIS, QGIS, ArcGIS, offer the approaches to digitize the riverbank lines and create these active river channel masks. But one of the key things to consider here is the uncertainty within each data set. So there's the potential to erroneously digitize some of the banks of the channel, depending on seasonality and lower quality images. And we also need to consider sources of error when geo-rectifying the images as well. So how well we can actually rectify the aerial images and the historical maps and consider the uncertainty analysis. And here we show an example of historical aerial imagery. We focus on the Bislett catchment and take an example from the town of Vintar. And we show an aerial photograph from 1947 and compare that to a contemporary image taken in 2020, a satellite image. We digitized the active channel area, the area shown in red here, in 1947, and compare that against the area shown in blue for the active channel in 2020. And it's really notable that we have substantial changes in position and shape of the Bislett River. So in 1947 it's a braided system, but we have two separate threads of the channel in the valley bottom. In 2020, the active channel area has been reduced to a single braided thread. You can see that to the north of the active channel, agriculture has been developed on the floodplain with some roads as well. And this is important because we can start to think about the river behaviour through time. So previously we've had multiple threads, the active channel area was larger, it seems to have been narrowed in recent times. And a really great source of information here was the National Archives and Records Administration, NARA, to collect some of these aerial photographs. So in addition to aerial imagery, optical satellite imagery is also a really valuable data source for looking at river planform change. With data available from the 1970s onwards, Landsat imagery is a really significant resource because of the archive length and repeat coverage for river monitoring. More recently, centre advancements have refined the spatial and temporal resolutions of available imagery, and this is generally all freely and openly accessible. So Sentinel-2 imagery, the imagery shown in the middle here, has a finer temporal resolution and a higher spatial resolution, so 10 metre pixel size than Landsat imagery, which has a 30 metre resolution. As well as that, synthetic aperture radar offers an alternative radar-based approach for remote sensing, and that can really help us to see through cloud coverage. But from a fluvial geomorphology perspective, the medium resolution imagery, the optical imagery, are especially useful for investigating large rivers at the landscape change scale. So you can see here some of the examples of the resolution of imagery and the features that can be detected in a river system. We focus on the Cagayan River, with the confluence of the Ilagan River, and we can really pick out nicely sediment and gravel bars at the tributary confluence. We can also see this using synthetic aperture radar, the SAR Sentinel-1 approach, where we can pick out the wetter part of the channel really nicely. And one of the key advantages of satellite remote sensing over aerial imagery is the availability of repeat imagery. So we have lots and lots of archival satellite images available, dating from the 1970s onwards, and we can look back through that image collection to understand changes in the river planform. So we can build image collections that contain tens or hundreds of images, stack these images to see how a river is changing through time. And just an example of the revisit times for some of these satellites, we have a 16-day revisit time for the Landsat series, whereas the Sentinel series, it's about a 10 to 12-day revisit time, depending on where on the Earth you are. Looking at the temporal archive, Landsat imagery dates back to the 1970s, and is still being collected at the present day with Landsat 8, whereas the Sentinel record is much shorter, from 2015 onwards. But we do need to be aware of suboptimal satellite imagery within this record, especially when working in the tropics. So you can see for a single year of Sentinel imagery here for the Bislett catchment, many of the images are influenced by cloud cover, and that can really limit geomorphic interpretation. And just to note that the temporal revisit times are reducing, so with commercial satellite imagery providers, it's now possible to get daily or even sub-daily data from some of these providers. So we're imaging the Earth's surface much more frequently and shifting towards continuous monitoring from remote sensing. So in the previous slide we spoke about the benefits of multitemporal analysis, and here we consider the benefits of multispectral analysis. We can use different band combinations from remote sensed imagery to indicate the abundance of features of interest. This can be vegetation or even open surface waters. An example for vegetation of the river channel, we can use the Normalized Difference Vegetation Index to produce maps for live green vegetation. So we use the near infrared band and the red band and do a normalized difference between these bands for a single image, and we can start to pull out the abundance of vegetation. So the browner areas, the lighter areas indicate a lack of vegetation in the active channel area, whereas the darker green colours indicate an abundance of live vegetation. Likewise, we can do similar approaches to look at the detection of open water in a river channel. So the darker blues indicate an abundance of open water, and the greys, the lighter colours, indicate a lack of water. And it's the combination of these band combinations, putting together different multispectral bands, we can start to classify the riverscape using satellite remote sensing. So in this example we bring together the NDVI and the NDWI to classify portions of the river with exposed gravel, water, vegetation, and delineate the vegetation boundary. So we can start to identify the active river channel. So much of the analysis that I've spoken about so far can be performed on a personal computer. What we're really interested in is scaling that analysis further to look at the national scale of the Philippines and beyond. And one way to do this is to use a cloud-based computing platform to run the analyses. So we're taking away the data processing tasks from a single PC and using cloud computing networks to perform the analysis. One example of this is Google Earth Engine, which includes a data catalogue of publicly available, freely accessible remotely sensed data, including the complete Landsat collections and the Sentinel collections. And in the past, we'd traditionally have to download individual image tiles, digitize these tiles manually, and this is a really time-consuming and inefficient process when dealing with large-scale data sets. So Google Earth Engine offers a transition to multitemporal, multispectral analyses at a larger scale. And if you've got any questions on this, I recommend signing up as a member of Google Earth Engine. There's lots of tutorials and practical sessions that can be run there, and it's a really intuitive user face. So now I'd just like to show a brief example of how we've been using Google Earth Engine to understand changes in the active channel in the Philippines. So we've been taking the Landsat data products from Landsat 5, 7 and 8 for the time period 1987 onwards. So this contains thousands of images that ordinarily couldn't be downloaded and manually worked upon. We need this cloud-based computing platform. We're removing the cloud from these images, producing an average image for each year of the system, classifying using those multispectral indices that I mentioned previously, and then exporting active channel masks for each portion of the river. So just to take a little of a closer look at the workflow, first of all we define an area of interest. So this is an example from the Cagayan River. We take all available Landsat imagery for a year of the system, and we apply a cloud masking procedure to remove any cloud, to mask out any cloud from each image. And then using these cloud masked images, we produce a temporal composite. So we bring together 50 images, for instance, and average each of the bands in the multispectral image to produce this temporal composite. So this should produce a cloud-free image for each year of data. Then, based on the cloud-free temporal composite, we can start to classify the wetted channel. So here we're pulling out the wet part of the river, so just the low flow channel. And in addition to that, we're using the multispectral indices to pull out the sediment, the alluvial deposits as well, that make up the bankfull channel extent. So it's the wetted channel added to the alluvial deposits, which is giving us this binary representation of the active channel. And this is working quite nicely for the meander here on the Cagayan. We can see we're picking out the active channel, combining the wetted channel and the alluvial deposits to get this extent of the channel. So in applying the workflow, we can start to quantify active river channel changes at scale. So we take two river systems on Luzon Island, the Bislak catchment in the northwest, the largest catchment, the Cagayan catchment in the northeast, both of which are prone to extreme hydrometeorological events, and we can start to quantify river channel change. So we take the trunk stream of each network and apply that active channel mask for each year in the Landsat record. So we've got this region of interest defined as the trunk streams over hundreds of kilometres of river, and we can start to see by how much the channel changes. First of all, focusing on the Bislak channel, we're focused on a downstream reach that we showed previously from some of the work from PAMI and some of the historic aerial imagery, and we can map out the active channel occurrence. So this is the frequency with which a pixel in the scene is being classified as the active channel, and we can visualize changes in the dynamics. So in this example, the darker blues indicate positions where the active channel is frequently occurring, and the lighter blues represent areas of change. So these are infrequently occurring and infrequently classified as active channel. And what we can see is that the active channel generally remains in the same parts than much of the downstream portion of the catchment. It wanders in the downstream section, so we've got some movement towards the outside of the channel. You can see this wandering braided system here. But what's really interesting are these secondary shoots of channel that come away and rejoin the channel further downstream. So this is infrequently occurring, and we're getting activation and disconnection of these secondary shoot channels. And that's what we picked up from the historic aerial images as well. So altogether, this really suggests that the Bislak River is quite a dynamic system with lots of geomorphological changes of river channel planform taking place over the last 30 years of data. So for the Bislak catchment, we gave quite a qualitative description of changes in the geomorphology, but here we try and quantify some of those active river channel change processes. So here we use the RivMap toolbox in MATLAB and take each of the years of data from 1988 to 2019 and look at how the position of the centerline of the river has changed. And what we can see that the darker colours indicate the more recent imagery, the lighter colours indicate the older positions of the river channel. And we can see that once we average this over the entire reach, the average erosion rate or migration rate is approximately 17.7 metres per year. But that really varies between different years, so we have temporal differences in the rate of migration. So at the low point in 1988, the migration rate was around 8 metres per year, up to a high of almost 40 metres per year in 2005. So the migration rate doesn't just vary through time, it also varies spatially. So different parts of the river system are migrating at higher rates than other parts of the system. We can see here a meander cut-off process taking place, and then meander expansion, lateral expansion of the meander through time. Likewise, we've got really complex morphodynamic activity at this section of the river channel too. So we're getting spatially heterogeneous shifts in active channel centerline. So we're getting meander expansion, erosion and accretion, and cut-off processes being recorded within the dataset. And what this really means is that we have a diversity of river channel changes across the catchment, and not all positions in the river channel are migrating at the same rate. And here we can start to look a little bit more closely at some of the really active parts of the Cagayan River. We compare an image from 1989 to 2019, and we can see real morphodynamic change at the meander cutoff here. But we can also see that parts of the river channel haven't really changed through time. So that indicates the spatially heterogeneous nature of river channel changes. As a visualization, you can see how the centerline shifts through time. Here each image is at 5-year intervals, and we can composite these images to really indicate the areas where most change and least change has taken place. You can see that parts of the river haven't really changed, yet other parts of the meander bend have shifted in position by over 1 kilometre. So we get real changes, real spatial changes in the rates of processes and the magnitudes of processes taking place. And it's really important to remember that not all parts of the river are changing or adjusting at the same rate. So you've got to really know your position of the river within the catchment and think about what's happening both upstream and downstream with any position. And I think it's really important here to consider some of the limitations and uncertainties of the data that we're using. So a critical relationship exists between the width of the river and the spatial resolution of satellite imagery that's suitable for analysis. So what that really means is that on the Landsat data we can't see narrow rivers. You can see here worldview and pan-sharpened worldview imagery. You can pick out rivers less than 30 metres in width. On the Landsat imagery we get in mixed pixels and we can't really see the river at all in this image. So we need to be considering applications to large river systems generally greater than 100 metres wide. In completing multitemporal analysis, we need to consider the extent to which geomorphic change is being detected. So we've got lots of different sources of uncertainty when we're classifying the images, and we're getting those mixed pixels at the edges of river systems. So what we're seeing as planform change is that more than just noise in the image classification. So there's a really interesting paper by Donovan et al. From 2019 that discusses whether we can actually see true geomorphic change and what levels of detection are needed to assess geomorphic change. We need to consider the transferability of analyses. So when we classify an active river channel in one portion of the world, can that be applied elsewhere? We also need to remember that rivers not only adjust in the lateral dimension, but we need to consider that vertical dimension too. We're not really considering that in the planimetric planform analysis. And it's always really important to remember that human interpretation is required as part of geomorphic analyses. So we can automate lots of different processes to give us ideas and representations of how the river is changing, but human interpretation is really needed to understand the behaviour of the system. And finally, I'd just like to recap a couple of the key take-home messages from this section of the lecture series. Hopefully I've shown that rivers are dynamic in the Philippines and that the active channel is changing quite considerably for some of these systems. We need to remember that river systems are more than just a wetted channel. One useful way of doing this is to consider the active river channel as a bankful indicator. We should be able to integrate lots of different sources of data. It's important to look back at historical maps, at aerial imagery and satellite imagery to extend the record length. And we really need to be respectful of the diversity of river forms and processes within a catchment. So both between reaches and within a catchment, there are lots of differences in the rates and magnitudes of channel mobility. So for any position in the river system, for any individual place, we need to consider what's happening both upstream and downstream. In the next steps, we'll move on to lecture 3, where we'll consider river migration explicitly at sites of critical bridge infrastructure in the Philippines. And then we'll move on to the practical session, which brings together the themes from lectures 1 to 3. Thank you for your attention, and we'll see you in lecture 3.